So we've talked some about waves in general now. We've talked about wave characteristics, wave properties, and what we're going to start doing is moving into talking about sound waves specifically. So we'll look at how some of those characteristics and properties apply to sound waves, and we'll also look at some phenomena that are specific to sound waves. So sound is a longitudinal wave. We talked about that before, and that basically means that the waving motion, the oscillations, are parallel to the motion of the wave. So we talked about the example of a slinky where you bunch it up and you send those pulses down the slinky and they're oscillating back and forth in the same direction that the wave is moving. And the way we get sound waves is really from any object oscillating back and forth in the air. In fact, if you take your hand and just push it back and forth very rapidly, in theory you are creating sound waves. They're just too low of a frequency for a human to hear. But when we get objects oscillating a lot faster, like this tuning fork here, which is going to be oscillating back and forth very rapidly, what that does is it creates sound waves. And really those sound waves are pulses or differences in pressure moving through the air. And so if you look at this chamber here, it's showing you how that sound wave affects the air. And we see that there are these spots where the air molecules, that's what those little dots represent, are very, very close together. That are spots of high pressure, okay? And then we have other spots here where the pressure is much lower and the molecules are very, very spread out. Okay, so those would be spots of low pressure. And that really is what a sound wave is this oscillation flowing through the air, a longitudinal wave, so it's oscillating in the direction it's moving. And it's really just a series of high and low pressures. And that's what happens when someone talks, when an instrument is played, when music is played. The air is oscillating back and forth as vibration sent through the air, eventually to your ears, and then you hear them as sound. Now, sound can travel through other mediums, but the one we're obviously most common with is sound traveling through air. So specific to sound waves, two characteristics we talked about before that I want to just talk about how they appear in sound waves are amplitude and frequency. So the amplitude of a sound wave determines the volume of that sound wave. The louder the volume, the more amplitude we have. Technically, amplitude for sound waves is usually measured in units of decibels. I'm sure you've heard this before. We're not going to get into the decibel scale for a number of reasons. But that is the common unit we use. Technically, we could use the unit for pressure, which is pascals, to measure it because it really just is a difference in pressure traveling through the air. Frequency is the other big quantity, and so when we're talking about sound waves, the frequency is what determines the pitch of a sound wave. So the higher the pitch, the higher the frequency. So humans in general can hear frequencies from about 10 hertz. All right, that would be like a very, very, very low note, all the way up to about 20,000 hertz, which would be like an ear-piercingly high pitch. All right, so that's the range of frequencies that we can hear, and the higher the pitch, the greater the frequency. All right, so sound, just like any other wave, the speed of it depends on the medium. So in air, sound has a speed of about 343 meters per second. The reason why we're saying about 343 meters per second is that is going to be at a temperature of 20 degrees Celsius, which is 68 degrees Fahrenheit. That is going to be at 1 atmosphere of pressure. And at some humidity, and I don't know what humidity they typically use to create that measurement, but the point is that the temperature, the humidity, the pressure, even the composition of the air, all of these things would affect that speed of sound through air. So if we go to a spot where it's low air pressure, like if we're on the top of a mountain, that would change the sound. If we change the temperature, if we change the humidity, if we release some gas into the air that's going to mix with the air, all of these things would change the speed. Sound can travel through other things. It doesn't have to be a gas like air. It also can travel through liquids and solids. In fact, it actually travels much quicker through liquids and solids. And a part of that is just that the molecules are closer together. And the way that sound propagates is by oscillating molecules that then interact with other molecules and get those oscillating. and then those interact with other molecules that get them oscillating. So in liquids and solids, when the molecules are closer together, it actually allows the sound to travel through it faster. So we have two quick conceptual questions here. If a person is singing off key, what needs to be changed about their sound wave? Off key, that really is dealing with the pitch, and so we would need to change the frequency of their sound wave if they're singing off key. And then the second one, a person that concerts standing far away and they want to hear the music sooner. In that case, we're really talking about how quickly that sound travels through the air. And so what do we need to change to make the wave travel faster so they will hear it sooner? And that would be, we need to change the medium. And if we want to be more specific, we could say the temperature, we could say the humidity, we could say the type of gas, although that obviously gets into some issues with breathing, but all those would change the speed at which the sound travels through the air. All right, let's do some math problems here. So an A note has a frequency of 440 hertz. What is the wavelength of this sound wave? So we're going to use our equation velocity is wavelength times frequency. We know for a sound wave the velocity is about 343 meters per second. You will see that on your equation sheet, and unless otherwise noted, that's what we'll go with for the speed of sound. It's a pretty good approximation at about room temperature. So that equals the wavelength times our frequency, which is 440 hertz. And so we solve for wavelength, and we find that the wavelength in this situation would be 0.78 meters, so just short of 1 meter. All right, so for this practice problem, we have two different waves here, and we're going to answer a bunch of questions based on these waves. So here we have graph A and graph B. The first thing we want to find is the frequency of each wave. So what I would notice is that both of them have time as their x-axis, which means we can use this graph here to determine the period, and then of course once we have the period we can get the frequency. So what I'm going to do actually is because of how this graph is marked, because it's relatively small times, I'm actually going to count how many total waves I have here within 0.06 seconds and use that to find the time for a single wave. So I have 1, 2, 3, 4, 5, 6, 7.5 waves. So if I think about that in a time of 0.006 seconds, I have 7.5 waves, which means that my period is going to be 0.0008 seconds for A. And I'm going to do the same thing here for B, and then we'll get the frequency of both. So with B, I have 1, 2, 3, 4 waves in that same time period of 0.006 seconds represents 4 waves. And so that means that the period for this one is 0.0015 seconds. And so from there I can go ahead and determine the frequency of each. So the frequency for A is going to be 1 over that period, which is 1 over 0.0008, and so we end up getting a frequency of 1,250 hertz. And then for B, we have a frequency here, which is 1 over the period, and we end up getting 1 over 0.0015 for a frequency of 667 hertz. The next question we're asked is which sound is louder? And the louder sound is going to be the one that has the greater amplitude. So if we see A goes up to an amplitude of about half a Pascal, whereas B goes up to a greater amplitude of about 0.8 pascals. So that means that B is going to be a louder sound. Which one has a higher pitch? That really is just a measure of which one has a higher frequency. So that is going to be A for choice C. And then for the last one, which sound travels faster? They're going to travel at the same speed. We are assuming that these are played within the same space, and therefore they have the same medium, and they would travel at the same speed. The problem probably should indicate that, but we'll just make that assumption and say that they are in the same medium, and therefore they're traveling at the same speed, even though their amplitude and frequency differ. So the last thing we're going to talk about briefly is just How some examples of how those four wave properties, diffraction, reflection, refraction, and superposition, apply to sound waves. Superposition in particular is going to be really, really important when we talk about music, and we'll get into that a little bit later. We're not going to do a super in-depth treatment of that, but we will talk about that some later. So we'll mention it for now, but then we'll dive a little bit deeper later on in the unit. So the first two, as I mentioned, superposition, we'll talk more about later with harmonics, but that's basically how multiple different sound waves combine to create a pleasant, complex, rich wave. Those of you that play an instrument or maybe sing probably know a little bit more about this already. Beats is something else we'll talk about. If you happen to play guitar, you probably tune your guitar using the idea of beats, whether or not you know it. That is one way of tuning a guitar, although I know some people just can hear the sound and know how to tune it based off of that. And then another great example is noise-canceling headphones. The way noise-canceling headphones actually work is they hear the sounds from the outside and they create an opposite wave that combines with destructive interference to cancel out the noise from the outside so that you only hear whatever you're listening to, music or maybe a movie on an airplane, through the headphones. Diffraction's a big one with sound waves. We talked about this before when we were introducing diffraction, but sound spreads out going through open doors, windows, etc. This is what allows you to hear someone that's speaking out through a door, even if there's not a direct line for the sound wave to go from that person to you, because those sound waves spread out as they go through those openings. And so you don't need a direct path because of this property with sound waves. The next one, reflections, echoes, is something you're all familiar with. That is just the reflection of a sound wave off of an object. So that's a pretty common one that you definitely know about. The last one, refraction, we do have some examples of refraction. There's not a great example, but one that you sometimes will see is particularly if you're out on like a lake relatively early in the morning when it hasn't really started to heat up too much yet. You end up with a situation like we see here where there's warm air above the lake, but then the lake is still cold, and so there's cool air right above the lake. And what ends up happening is that causes the sound waves to bend. And so the effect is that you actually can carry your voice very, very well over the lake, because all the sound waves that are initially going up like that, they're going to bend back down, okay, because of refraction. And so it helps to direct a lot of these waves. It helps, a voice to carry much further than it normally would when this is not the case. Kind of a stretch there. We're not going to talk a ton about refraction with sound waves, but that is one example of it, and we could find other examples if we really looked.